Sure.
Yes. And perhaps you can start. Well, I think that uh, people present know you and also Jackson, but could you introduce your co-author, please? Is he your student or she? I don't know, he or she.
Yeah. So yeah, thank you, Janusz, for giving the opportunity to talk at the formal seminar. So I want to talk about this project on realizations through weakly reversible networks and the globally attracting locus. And this is joint work with my student Samay and Jashin. Jashin is now an assistant professor at University of Louisiana at Lafayette.
Mhm.
Yeah, so he was a PhD student with George, and then he did a postdoc with Marty Golubitsky at Ohio, and now he's at University of Lafayette. And Samay is my student.
Yeah, okay, yes, thank you.
Okay. And all right, so let's get started with the talk. So I think, I mean, most of the things are known to this audience, but just for completeness, let me very briefly go through details. So, of course, I mean, it's well known that biochemical networks are known for their sophisticated behavior, and much of the explicit behavior is exhibited by lots of reactions that go inside such networks, and they are often mediated by catalysts, by enzymes which alter kind of the rate and specificity of the reaction. Right? And the main focus, the features that are responsible for these things are the structures of the underlying networks that are part of those big structures. So, for example, the most basic things involve, for example, hydrogen and oxygen, let's say, combine to give water. Then you can intuitively define a reaction network as a tuple of sources, complexes, and reactions. And for economical means, you can just represent them as sources and reactions because you can recover complexes from sources and reactions. So, and
Just one moment, excuse me. It's only a remark. My chemical friends emphasizes that we are mainly speaking really with biochemical reactions because we usually are not interested in the atomic structure of the species. And chemistry starts when there are changes in the number of atoms, but usually we don't deal this part. So it's not your fault. I just mentioned this. Thank you. Sorry.
yes, you're right. So, I mean, I wanted to give a more realistic example, but yeah, you're right that this was just the most common example. So, again, these are reactants and these are products, and the rate in which uh, if you assume the most common assumption in chemistry, which is standard deterministic kinetics, which says that the rate at which the reaction occurs is proportional to the concentrations of the reactant species. So uh, if you have a generic reaction like this with x1 plus x2 giving you x3 plus x4, then the reaction rate is given by k times x1, x2. So what's important here is that the rate of the reaction is proportional to the product of concentration of the reactants. And what occurs is essentially just the monomials corresponding to the source vertices. Okay, so I'll come back to this later, but just to keep this in mind. And this will be our usual assumption. And a more geometric way of viewing this is this Euclidean embedded graph, right? So you can think of reaction as a graph where each each uh, each reaction is some sort of edge, a directed edge in this graph. So you can define this as a tuple v comma e, where v is a set of vertices and E is a subset of this Cartesian product. V cross V is the set of directed edges. And this geometric way of viewing reaction networks gives insights which are going to be eventually helpful in determining the dynamical inclusions between different types of networks, right? So, for example, one of the most famous networks that people study is this prey-predator model or some kind of Lotka-Volterra network. So you have these three reactions where you have x goes to 2x y goes to 0 and x plus y goes to 2y. And this is the standard preparator thing where you can see oscillations or limit cycles or some kind of all these exotic effects that come into picture, right? And you can describe this as a graph, right? So each reaction is a vector, and then you can talk about the linear span of those vectors and the subspace formed by this reaction vector, right? So that's what I'm going to do next. So, but just to give you an idea of what kind of dynamics networks can exhibit. So if I just take, for example, this triangle, this weakly reversible triangle with actually any choice of rate constants, then you can see that, in fact, there is a globally attracting steady state that is the dynamics corresponding to this network. And in fact, it does not matter actually here in which case what rate you put because of the deficiency zero theorem. So essentially, you always have this globally attracting steady state. And if you make, for example, the network slightly more complicated with this step, so I have this reversible reaction, a reaction that goes down and here, and then you have another, this kind of step-like network. The dynamics is a bit more exotic. So you have essentially stable and semi-stable states. So the steady states that you see on the boundary are stable. And the steady state that you see in the middle is a semi-stable steady state. It has two directions which are converging towards it and two which go out of it. But now something interesting happens if I add an extra reaction here. So I don't take the same triangle, but I kind of flip the triangle and I add this extra parallel reaction to this triangle. And then again, you can see that this gives rise to a stable limit cycle, right? So trajectories inside this limit cycle merge towards this red limit cycle, and trajectories outside also converge to this cycle, right? So just by tweaking networks and playing with this geometry can lead to very exotic dynamics. And one of the motives of this talk is to explore these dynamical connections between many types of networks. So, all right, and so just standard terminology. So I guess most of you are already aware, but the set of vertices in the network can be partitioned by its connected components, which are called linkage classes. And those linkage classes can be identified by the subset of vertices that belong to that connected component. So for each linkage class, I just identify by the set of vertices that it contains. All right. And you say that a network is weakly reversible if every edge in any linkage class is part of a directed cycle, right? Or another way of saying this or rephrasing this is every connected component is strongly connected. And this is the notation that I'll be using throughout the talk. So please note this notation that G, I say subset WR G prime, will denote that G is a weakly reversible graph of G prime, right? So G is a subgraph, which means its set of vertices and edges are a subset of the set of vertices and edges of G prime, but further, G is also weakly reversible. So this symbol will be used to denote this. And I'll be using this quite frequently in the remainder of the talk. Right? So basically, just coming back to this, the actual rate formation function. Sorry? Yeah. To the rate formation function. So if you have K, which is the vector of rate constants, and if you have the mass action kinetics, then you know that the ODE can be kind of rephrased as this rate constant times the monomial times this reaction vector between the species and the reactant. And I think what is the most important thing about mass action kinetics is that this Y that you see here is the same Y that occurs in this rate, right? You don't have a different Y. The Y's match in the rate and in the monomials, right? So this will be our assumption. And from there, as I said, thinking of reaction networks as graphs, you can imagine the vector space spanned by the reaction vectors, which is the stoichiometric subspace. And that is the span of all reaction vectors. And for every positive vector x naught, this set x naught plus s intersected with the positive ortho, all affine translates of this stoichiometric subspace is called the stoichiometric compatibility class, or the affine invariant polyhedron, right? It's affine because you take an affine translate, and it's invariant because for mass action kinetics, once you start in this polyhedron, you're confined within this polyhedron. So it can be shown that this polyhedron is invariant. And with this terminology, we can now write down the whole Lotka-Volterra system, which I guess most of you are aware that you can write down this system, which I didn't write the ODs in explicitly in full generality. Then you have this k1 times x1 times this vector corresponding to x goes to 2x. Then similarly, you have the rate function for this times this vector plus k3 times this vector. x2 is for y times this vector. Right, so this is the rate equation for this Lotka-Volterra model. All right, so now I think coming to the main title of the talk, one of the key phenomenon that is important in the context of reaction networks is dynamical equivalence, right? So what's the meaning of this term? So intuitively, it just means that it's possible for two different networks, completely different networks with different structures and different arrangements, to generate the same set of dynamics, right? So, and one way of kind of making this formal is to say that for every vertex in the union of the two vertices, so if I take two mass action systems, GK and G prime K prime, they're said to be dynamically equivalent if for every vertex Y0 in this V union V prime, you can show that the net flux out of this vertex with respect to the graph G is equal to the net flux out of the vertex Y0 with respect to the graph G prime, right? So note that the monomial x to the Y0 does not appear in this equation because it just gets cancelled on both sides. But there's another way of saying that two systems are dynamically equivalent. And we'll use this notation, this similar symbol, to denote the fact that two systems are dynamically equivalent, right? And for example, this is an example. The figure that you see in red is just one source. Sorry?
No, sorry, I didn't realize that my mic was on. Sorry.
Oh, okay, yes. All right. So the one, this is just one vertex with two rate reactions, and you can see that if you just keep the rate constant the same, I mean, this is a very simple example, but it kind of illustrates the idea that for more complicated networks, you can tweak the network structure and still generate the same set of differential equations, right? For our talk, we will actually need a slightly general notion of dynamical equivalence, which we would like to call dynamical inclusion. So dynamical inclusion is slightly more general than dynamical equivalence in the following sense. So let's say we take two networks, then the dynamics of G, we say that it's included within the dynamics of G prime. If for any choice of K on G, you give me any choice of rate constants on the graph G, you can always choose, there always exists a choice of rate constants K prime such that GK is dynamically equivalent to G prime K prime, right? So this is not the same as dynamical equivalence. It's a kind of a more generic notion, which means that no matter which choice of K you make on the original graph G, you can always choose some K prime on G prime such that you can make both these have the same set of ODs. And this brings us to kind of the main question of this talk, which is, suppose someone gives you a graph G, right? Under what conditions can you say that there exists a graph G prime, which is weakly reversible, and G prime includes the dynamics of G, right? So we'll use this reverse square symbol to denote the fact that the dynamics of G is included. I mean, it's not a subset symbol, but included within the dynamics of G prime. And the particular question that is of interest is, under what conditions can the dynamics of a graph G be included in the dynamics of some weakly reversible network? So that's the main question of this talk. And of course, I mean, there are infinite many possibilities, right? There are many weakly reversible networks that you can think of, and the dynamics of that can include the dynamics of this given graph G. But it turns out that we need to focus only on those weakly reversible networks, which are weakly reversible subgraphs of this graph GC. So this graph GC refers to the complete graph on the source vertices of G. So because of some result by George, Pauly, and Jasheen, it turns out that you need to focus only on a finite number of weakly reversible subgraphs, not all possible weakly reversible subgraph, but only those which are weakly reversible subgraphs of the complete graph on the source vertices of G. But still, how do you know that such a graph exists, right? So the question is, how do you know even within this finite subset, how do you know that one exists such that if you put an appropriate choice of K, you can always generate any possible dynamics on the given graph G? So that's the question that was there. And to kind of answer this question, I wanted to introduce one more family of networks, which are called endotactic networks, right? So the word endo means inward pointing and tactic means taxi. So the idea of these networks was that these networks point inwards in some sense. And they were introduced by George Kasian and Fedor Nazarov in about a decade ago. And as the name suggests, they are inward pointing and their dynamics is conjectured to be permanent, right? So it is conjectured that the dynamics of endotactic networks, there exists a compact set such that all trajectories kind of eventually converge into that compact set. And in dimensions 2 and in some special cases, it has been shown that it's actually permanent, right? And that kind of proves the global attractor conjecture in one dimension higher. So this idea of endotacticity, persistence, permanence is one of the key things in kind of the proof of some special cases of the global attractor conjecture. So let's have a look at what does it mean to be endotactic, right? So if you look at this figure A and B, right? Let's look at this network in figure A. The dotted line is essentially the boundary of the convex hull of the source vertices of the network, right? So, I mean, you have source and a target, everything points inwards, but what joins them is this boundary of the convex hull of the source vertices. And what you see there is the red arrows. These are essentially inward pointing normals, which you can use to determine whether a network is endotactic or not. And this test is called the parallel sweep test. So what it means is that imagine that you come in the direction of this red arrow. Let's pick this red arrow. Okay. I mean, you can choose any one, but let's pick this red arrow. Then you hit this boundary of the convex hull. And then you see that all reactions point strictly inwards. They point in the direction in which you are sweeping. There is no reaction that points opposite to the direction in which you are sweeping. And because of that, this network is endotactic. Let's take figure B. Figure B is a bit more subtle because let's take this direction, for example, this direction that goes from south to north. And then when you hit this first reaction here, there is no reaction that points inwards, or there is no reaction that points outwards. There is nothing that happens basically because this network is perpendicular to this sweeping direction, right? This black line is perpendicular. Then you keep on sweeping. If there is nothing that points outwards, then you keep on sweeping until you hit this again. Now, again, this upper horizontal line is again perpendicular to this red sweeping direction. So still, it's fine. We still cannot conclude endotacticity, but we keep on sweeping and then we reach this vertex. And at this vertex, we see that there is this reaction that points inwards in the direction in which we have set. So even if this happens, we call the network endotactic. And for strong endotactic, you need that there should be a reaction that points strictly inwards at the first point of contact at the convex hull, right? So this network in B is endotactic, but it's not strongly endotactic. And this network in C is not endotactic, because no matter where you come from, no matter which direction you come from, there are these reactions that point outwards, right? So we now have all the key things that we need for our theorem. We want to know when can a dynamics of a network be included within the dynamics of a weakly reversible network. So our first kind of mini result is what's a necessary condition for the dynamics to be included in the dynamics of some weakly reversible E graph. And it turns out, not rather surprisingly, that the condition is just that G is endotactic. So this is the answer. Endotacticity is necessary for the dynamics of any E graph to be included within the dynamics of some weakly reversible E graph. So if you don't start with an endotactic network, you can never imagine having a weakly reversible graph that can generate or include the dynamics of your starting graph. And this is quite nice because you can use this to eliminate all networks for which you know that you cannot have a weakly reversible realization, because you need endotacticity for sure. This is a necessary condition. And the proof involves some ideas from this net reaction vector. So, I mean, I'm not going to show you the whole proof, but kind of just give you the idea and the flavor behind the proof. So there is this notion of net reaction vector associated with each vertex. And what is this net reaction vector? Well, you look at the flux that comes out of the vertex y, right? So which means ky to the kyy prime, that's the rate constant, times the monomial times the reaction vector, but you exclude the monomial. So you take all the terms that kind of go out of y, that kind of emerge from y, but you leave out the monomial x to the y. So for each y, this wy stands for the net reaction vector. And it turns out that if you kind of generate this as an intermediate step, this E graph corresponding to the net reaction vectors of E, it turns out that you can use this information to conclude that endotacticity is necessary for the dynamics to be included in the dynamics of some weakly reversible graph, right? So how do you generate this E graph corresponding to this net reaction vector? Well, you take the same sources as G. So in this graph for the net reaction vector, you take the same source vertices as you had for G, but the target vertices are chosen differently. The target for each source vertex, you choose a target vertex, there exists a corresponding target such that this reaction vector y prime minus y is exactly equal to this net reaction vector wy, right? So all I'm trying to say is you can use this net reaction graph as kind of an intermediate step to conclude that endotacticity is necessary. And that gives us our first main result, that the idea is that if I have two mass action systems such that they're dynamically equivalent and G prime is...
Excuse me, Abhishek, could you go back, please? I couldn't follow you. Why don't you define y hat in such a way that is simply y plus wi? Why? So
yes,
y hat is just the sum of these two vectors.
Yes.
Why is it wrong?
No, it is fine. That's how you define. You can choose a y, yes, such that y hat is y plus w. You're right. That's how you choose the y hat.
So I don't know, why do you say that exists? Because if we simply say that let y hat be equal to y plus wi.
Yes. I mean, you could say that, but you're right. Y hat is just y plus wi. Yes. Maybe I just didn't phrase this correctly. Yes.
Okay. Thank you.
Yeah. And so, as Janos said, this is a deterministic procedure. Y hat is just y plus the wi. And so if I have two dynamically equivalent networks and G prime is weakly reversible, I can show that this network corresponding to the net reaction vectors is endotactic. And I can use this information with a few more steps to essentially conclude that the network G must be endotactic to start with if its dynamics has to be included within the dynamics of a weakly reversible E graph. So this is the key step that is required for the dynamics to be included in the dynamics of an E graph. Right? So this is our first kind of one of our first main results, that the necessary condition is you start with an endotactic graph. Otherwise, you cannot do anything. But what about sufficient conditions? Can you kind of find under what conditions that the dynamics of graph G be included within the dynamics of a weakly reversible graph G1? And a partial answer to this question was given by this paper in David Anderson, George Krachun, Matthew Johnston, and Jim Brunner. It was this paper. I mean, I'll come to this figure later, but it was this paper on classes of reaction networks. So they found this condition that if you start with a strongly endotactic two-dimensional graph with two-dimensional subspace, and all vertices lie on the boundary of the convex hull of your Newton polytope. That's the convex hull of the source vertices. Then you can always guarantee that there exists a weakly reversible graph which includes the dynamics of your network. So this was the starting point. This is not our result, but we tried to improve upon this result by giving slightly different conditions, sufficient conditions. So our sufficient conditions are at least one of these things hold. So either all source vertices lie on the boundary of the Newton polytope of the convex hull of the source vertices, or there exists a source vertex on the boundary of the convex hull such that the net reaction vector corresponding to that vertex points strictly in the interior of the Newton polytope, right? So this is an extension with, so it's if and only if, so that's the other extension, but the second condition is the new contribution. And it proves a stronger theorem that the weakly reversible network that it generates actually has single linkage class, right? So it extends this result in kind of several ways, but their result was the starting point behind this analysis. So they were the first ones to do this. So, I mean, this is also a thing from their paper. This is not my figure, but I'm trying to explain the key idea behind the sufficient conditions from this figure. So what you see in figure A is a strongly endotactic graph. Basically, what you have is with two-dimensional subspace, all source vertices lie on the boundary. Like there is no source vertices that lies in the interior. And there exists this vertical vector. You see this vertical vector in figure A. So you have this vector that I was referring to, the second condition. You have a vector on the boundary such that the net reaction vector points strictly inside. And after a series of some complicated procedure, you can show that the network in figure D is actually a weakly reversible network. So you do a sequence of operations, slightly complicated operations, and you can show that you can always go from A to D, and D is a weakly reversible network. So as long as you have a strongly endotactic network with nice properties, you can guarantee that there exists a weakly reversible, in fact, single linkage class network that contains the dynamics of your original network. So this was one extension. But now question, this was only in 2D, right? If you notice this, I just said this start with this 2D case. This is just a 2D graph. What happens in higher dimensions? And in higher dimension, things get quite complicated, right? So this limitation is illustrated in the following figure. That imagine this cube, right? This cube is a 3D kind of network with a very peculiar property that if you look at this red vertex, the vertex that is here, it has reactions that go out of the vertex, but there is no way to reach the red vertex. There is no way to kind of modify any other vectors, add, subtract vectors, do any kind of modification to go back to this red vertex. So there's nothing you can do to generate a path from any blue vertex to go to the red vertex, right? There's nothing that can be done in this example. And that illustrates that you need something stronger. You cannot just say strongly endotactic. I mean, this is strongly endotactic with all source vertices on the boundary, but it fails in higher dimension. It only works in dimension 2 because it's a planar structure and you can play with the convex hull and do this sequence of operations. But for higher dimensional networks, this fails. And you need a much more sophisticated condition to handle this kind of dynamical inclusion. And what you need is the following. So for each linkage class, you collect all the terminal strong connected components, right? And what you need is that for every terminal strong connected component, there exists a vertex within that strong connected component whose net reaction vectors points inside the interior of the Newton polytope of that linkage class. Okay. For simplicity, I just drew this figure, which is a replica of the previous figure, but with this extra arrow. You see this arrow that goes from this bottom vertex, and that points in the interior of the cube. And that is how you resolve this problem, because you can split this vector that points in the interior of the cube so that it goes to this vertex, to this red vertex that I was talking about. But you need to do this in a minimal sense. For each linkage class, you need the net reaction vector to point kind of strictly inwards within the Newton polytope of the linkage class. And then again, you can play this game in higher dimensions and establish that you can always generate a weakly reversible graph, which kind of includes the dynamics of your original graph, right? So at the moment, we have solved two questions: necessary and sufficient conditions for dynamical inclusions in a weakly reversible graph. And now I want to move on to how all of this is related to something in algebra, right? So this notion of toric locus, the disguised toric locus, and globally attracting locus, right? So let's see how all of this is kind of, how dynamics is related to some stuff in algebra. So what we know what's a steady state, right? A steady state is just a point where the ODE evaluates to 0. So this mass action system evaluates to 0. But what we are interested in is the complex balance steady state, right? So a positive state is complex balance if the net flux that goes out of this vertex y0 is equal to the net flux that goes into y0, right? So you have this kind of flux balancing at every vertex y0. And if that happens, then we say it's complex balance. And of course, if it's known from theory of Feinberg, Horn, and Jackson that if you have a complex balance steady state, then all steady states are complex balance. And the resulting dynamical system is called toric dynamical system, right? So this was the name given by George, Alicia, Bernd-Stumpfels, and Ann Chu, this 2010 paper, which I'm going to come to. So for example, just to kind of be clear what complex balancing means, you imagine this graph and imagine that all the fluxes on each reaction vectors, they are kind of balanced at each vertex. So the sum of fluxes that go out of each vertex is equal to the sum of fluxes that go into each vertex. And so this is an example of a complex balanced system. All right. So now question is, what can you say about the algebra of complex balance systems? You want to know what's the locus in the set of rate constants for which the dynamical system generated by this GK is toric, right? So this is the toric variety that you want to analyze, or the toric locus of this system. And it's known that, of course, if G is weakly reversible, then this toric variety is non-empty. And if it's not weakly reversible, then this toric variety is empty. So weak reversibility is needed to kind of effectively study this variety. And what's the dimension of this variety, right? So in this paper by Alicia, Bernd-Stumpfels, George, and Ann Chu, they established that you can actually relate the dimension of, or the codimension of the toric variety with this quantity called deficiency, which is this number of vertices minus linkage classes minus the stoichiometric subspace. But before I go to that, there is a small subcase which tells you when is this toric variety full, right? For if all choices of rate constant satisfy complex balancing, and that happens if and only if your network is weakly reversible deficiency 0. right? So that's the content of the classical deficiency zero theorem. And and of course, so if you have such a network which is weakly reversible deficiency zero, then it's complex balanced for any choice of rate constants, right? And therefore, you have a unique globally attracting equilibrium because it's in 2 dimensions and all robust dynamical properties follow. But as I said before, the codimension of this toric variety is given by this deficiency. So if you see, the dimension is E minus the deficiency. So the codimension is given by deficiency. And so that's the toric locus, right? But I want to talk about a bit more complicated algebraic object, which is this disguised toric locus. So I want to define a bigger variety, a bigger semi-algebraic set, which is disguised toric, which means that the network itself is not complex balanced, but the ODEs generated by this network is dynamically equivalent to a complex balanced network. So I have a bigger semi-algebraic set than this toric variety, for which the network itself may not be complex balanced, but the ODEs generated by it give rise to a complex balanced system. And in fact, it contains this toric locus, right? So this defining this requires a bit more care. So let's try to see what this semi-algebraic set is, right? So I say K disk stands for disguised. I take a pair of graphs, G comma G prime. And I say that the set of all K for which the dynamical system is disguised toric on G. What it means is that the dynamical system generated by GK is essentially can be generated by some complex balance system on G prime, right? So I take 2 graphs, G and G prime. How do I choose G prime? Well, I choose G prime to be only those weakly reversible subgraphs of the complete graph on the source vertices of G, because of the reason that I mentioned earlier, right? So for each such pair, G graph is a weakly reversible subgraph of the complete graph. I calculate this quantity, right? So this is for a pair of such graphs. And this semi-algebraic set, the disguised toric locus, is the union over all such weakly reversible subgraphs, right? So I repeat this over all possible weakly reversible subgraphs. I take the union of all such semi-algebraic sets. And this bigger locus is this disguised toric locus, right? And I think what we have been doing over the past year or so have been trying to kind of analyze this disguised toric locus, kind of calculate this, the dimension of the disguised toric locus. But in this case, the idea would be to relate this weakly reversible and endotactic realization. So how is this algebraic structures related to this, right? So I just need to introduce one more notation before I come to my main theorem. So I know what the toric locus is. I know a bigger set, which is this disguised toric locus. And I want to define a slightly different set, which is called the globally attracting locus of G, right? And this semi-algebraic set is the set of all Ks such that the mass action system generated by Gk has a globally attracting steady state within each stoichiometric compatibility class. So it means that it's the set of all K for which you have globally attracting steady states. And this is important, right? Because it would be nice to have conditions under which you can deduce, oh, if I just look at this network and I want to know, does there exist a choice of rate constants for which there are globally attracting steady states, right? So can I have sufficient conditions to kind of determine whether a given network can have globally attracting steady states? And we answer this question in a very limited setting under some specific sufficient conditions. So just to introduce this, I just want to introduce one more notion, which I'll be using in my analysis, which I have been talking about. So this notion of flux vector, right? So I have this flux vector where for each reaction, you can calculate this flux, which is this rate constant times this monomial. And if you collect all those fluxes, you get this flux vector. And you can rephrase this condition of complex balancing in terms of this fluxes. So the net flux that goes into Y0 is equal to the net flux that goes out of Y0. And the advantage over this complex balance condition, I mean, it's the same, it's equivalent, but the advantage is if you deal with fluxes, then this becomes a linear condition, right? And this is exactly what we are going to exploit the linearity of this flux condition to kind of impose sufficient conditions under which the globally attracting locus of a reaction network is non-empty, right? So can you use this linearity of this fluxes to guarantee that there are certain networks for which you can generate globally attracting steady states. And it turns out that to kind of determine whether the disguised toric locus of a reaction network is non-empty, you need to solve a linear program. I mean, what you need to solve is, given an E graph G, I consider the complete graph GC, the complete graph consisting of all possible edges between all possible vertices. And the question is to find a flux, and a flux on G and a flux on GC, such that the net flow out of Y naught for each vertex for G is the same as the net flow for each vertex Y naught for G prime. So the first condition is dynamical equivalence. And the second condition, equation 3 that you see here, is the condition for complex balancing. The net flux on G prime out of Y naught is equal to the net flux into Y naught, right? So you need to solve some kind of linear program. And if you can solve that for a certain family of networks, you know that the disguised toric, this semi-algebraic set, which is larger than the toric locus, is non-empty. And you can combine this with certain reaction network structures to kind of conclude that the globally attracting locus is non-empty. So that's the content of the last theorem that I want to talk about, which is this, that if I have an endotactic E graph, right? So I'm using the assumption from my previous result, the first result, which said that endotacticity was necessary. So I can only talk about the dynamics being included in a weakly reversible graph only if I start with an endotactic graph. So if I have an endotactic graph, but I only consider endotactic graphs in two-dimensional subspace, and I just solve this linear program, a very simple linear program, then without solving the ODs, I can directly conclude that the globally attracting locus is non-empty. So that's the strength of this theorem, right? So for example, let me illustrate the power of this theorem on two biologically relevant examples, right? So how can you actually use this in practice? So imagine that you have this network that you see in figure A, right? How can you use everything that we have learned so far to good effect? So this is a very popular network. It's called one of those networks called Thomas type models, which essentially models the oxidation of uric acid by oxygen, which is catalyzed by the enzyme uricase, right? So this is a biologically relevant system, all right? So and what you see in figure B is one candidate weakly reversible subgraph of the complete graph on A, right? You can choose any, but I just chose one for illustration purpose. And now I use this theorem. I know this, okay, first of all, I know this is endotactic. This network is endotactic to start with. It's two-dimensional. And I just check these 4 lines. I just solve a linear program on the fluxes. And no matter how complicated my network is, without looking at this, but just by solving this linear program, I can conclude that my globally attracting locus is non-empty, right? In fact, how it works is that because the disguised toric locus is non-empty, and since it's two-dimensional, the globally attracting locus includes the disguised toric locus. And I can use this to good effect to kind of solve much more complicated examples and say that there exists a choice of rate constants for this network, right? Before solving this analysis, it was difficult to gauge how to do this, but now using this theorem, we can say that there exists a choice of some K on these networks for which this has globally attracting steady states, right? So that's the power of this analysis. And we also could show it for another classical biological model. This is this modified Selkov model. So these models are used in glycolysis, which are processes where glucose is typically broken down into pyruvate. So what you see in figure A is some kind of Selkov model, and figure B is again a weakly reversible subgraph of this graph in A. And again, this is endotactic. And again, by solving a very simple linear program, just by solving this linear program, again, we are able to conclude that the globally attracting locus is non-empty. So we know that this has globally attracting steady states. And you can do this even for more complicated networks. I mean, I mentioned this because these were biologically relevant, but even for more complicated networks, you essentially just need to solve a linear program under some additional constraints. And without solving the ODs, you can conclude that this semi-algebraic set of globally attracting locus is non-empty. All right, so I think that concludes my talk. So in summary, just to summarize, we started out with how can the dynamics of a network be included in the dynamics of a weakly reversible E-graph. And then we found out necessary conditions for this to be true is this initial network to be endotactic. And then we saw sufficient conditions for the dynamics to be included. And we kind of had to have some more sophistication between two-dimensional cases and stuff that kind of did not work in higher dimensions. And we saw how we could use all of this to our advantage to make statements about the toric locus, the disguised toric locus, and finally, the more important globally attracting locus, to conclude that that is non-empty. So a further question would be, can you impose conditions for which this globally attracting locus could be an open set? And how big is this open set? Can you find a huge space such that the dynamics generated by this network has globally attracting steady states? Right? So this kind of all intertwines together with this analysis of reactions and some algebra of this toric and disguised toric loci. All right, so I think that comes to the end of my talk. And so this paper is here, it's on arXiv, it's in review. And these are other papers that were kind of used in the analysis of this. And as I mentioned, that this other paper, which we have been working on to find the dimension of this disguised toric. So I think part 1 is already accepted by SIAGA Journal on Applied Algebra and Geometry, and part 2 is also on review. And yeah, I think these were my references. And thank you so much for your attention.
Thank you, Abhishek.